Synchronizers. The synchronizer performs a number of jobs vital to transmission, or transaxle operation. Its main job is to bring components that are rotating at different speeds to one synchronized speed. A synchronizer ensures that the pinion shaft and the speed gear are rotating at the same speed. The second major job of the synchronizer is to actually lock these components together. The end result of these two functions is a clash-free shift. In some transmissions, a synchronizer can have another important job. When spur teeth are cut into the outer sleeve of the synchronizer, the sleeve can act as a reverse gear and assist in producing the correct direction of rotation for reverse operation. In modern transmissions and transaxles, all forward gears are synchronized. One synchronizer is placed between the first and second gears on the pinion shaft. Another is placed between the third and fourth gears on the main shaft. If the transmission has a fifth gear, it is also equipped with a synchronizer. Reverse gear is not normally fitted with a synchronizer. A synchronizer requires gear rotation to do its job, and reverse is selected with the vehicle at a stop. Synchronizer design. Refer to this figure. The most commonly used synchronizer is a block or cone synchronizer. The synchronizer sleeve surrounds the synchronizer assembly and meshes with the external splins of the clutch hub. The clutch hub is splined to the transmission pinion shaft and is held in position by a snap ring. A few transmissions used pin-type synchronizers. The synchronizer sleeve has a small internal groove and a large external groove in which the shift fork rests. 3 slots are equally spaced around the outside of the clutch hub. Inserts fit into these slots and are able to slide freely back and forth. These inserts, sometimes referred to as shifter plates or keys, are designed with a ridge in their outer surface. Insert springs hold the ridge in contact with the synchronizer sleeve internal groove. The synchronizer sleeve is precisely machined to slide onto the clutch hub smoothly. The sleeve and hubs sometimes have alignment marks to ensure proper indexing of their splins when assembling to maintain smooth operation. Brass or bronze synchronizing blocking rings are positioned at the front and rear of each synchronizer assembly. Some synchronizer assemblies use frictional material on the blocking rings to reduce slippage. Each blocking ring has 3 notches equally spaced to correspond with the 3 insert keys of the hub. Around the outside of each blocking ring is a set of beveled clutching teeth, which is used for alignment during the shift sequence. The inside of the blocking ring is shaped like a cone. This coned surface is lined with many sharp grooves. The cone of the blocking ring makes up only 1/2 of the total cone clutch. The second, or matching half of the cone clutch, is part of the speed gear to be synchronized. As shown in this figure, the shoulder of the speed gear is cone-shaped to match the blocking ring. The shoulder also contains a ring of beveled clutching teeth, designed to align with the clutching teeth on the blocking ring. Operation. When the transmission is in neutral or reverse, the first, or second, and third, or fourth synchronizers are in their neutral position, and are not rotating with the pinion shaft. Gears on the main shaft are meshed with their counter-shaft partners, and are freewheeling around the pinion shaft at various speeds. To shift the transmission into first gear, the clutch is disengaged, and the gear shift lever is placed in first gear position. This forces the shift fork on the synchronizer sleeve toward the first gear on the pinion shaft. As the sleeve moves, the inserts also moves because the insert ridges lock the inserts to the internal groove of the sleeve. The movement of the inserts forces the blocking ring's coned friction surface against the coned surface of the first speed gear shoulder. When the blocking ring and gear shoulder come into contact, The grooves on the blocking ring cone cut through the lubricant film on the first speed gear shoulder, and a metal-to-metal contact is made. The contact generates substantial friction and heat. This is one reason bronze or brass blocking rings are used. A non-ferrous metal such as bronze or brass minimizes wear on the hardened steel gear shoulder. This frictional coupling is not strong enough to transmit loads for long periods. As the components reach the same speed, the synchronizer sleeve can now slide over the external clutching teeth on the blocking ring, and then over the clutching teeth on the first speed gear shoulder. This completes the engagement. Power flow is now from the first speed gear, to the synchronizer sleeve, to the synchronizer clutch hub, to the main output shaft, and out to the drive line. To disengage the first speed gear from the pinion shaft, and shift into second gear, the clutch must be disengaged as the shift fork is moved to pull the synchronizer sleeve, and disengage it from the first gear. As the transmission is shifted into second gear, the inserts again lock into the internal groove of the sleeve. As the sleeve moves forward, the forward blocking ring is forced by the inserts against the second friction surface, on the second speed gear shoulder. Once again, the grooves on the blocking ring cut through the lubricant on the gear shoulder, to generate a frictional coupling that synchronizes the speed gear and shaft speeds. The shift fork can then continue to move the sleeve forward, until it slides over the blocking ring and speed gear shoulder clutching teeth, locking them together. Power flow is now from the second speed gear, to the synchronizer sleeve, to the clutch hub, and out through the pinion shaft.